Welcome back, everybody, to our second talk for today. So this talk is going to be by Aoi Wakuda, and it's going to be on separability criteria for two loops on an orientable surface and the Goldman bracket. Take it away, please.
Thank you very much for the kind introduction. I am Aoi Wakuda from the University of Tokyo. My research field is low-dimensional topology. In particular, I am interested in loop operations on surfaces and the algebraic structures arising from them. Let me start with a quick quiz. Consider this question. Is it possible to separate alpha and beta by homotopy? At first glance, deciding whether they can be separated by homotopy does not look easy. The main purpose of today's talk is to show how we can determine this, whether they are separable or not, by algebraic calculations. Let S be a connected oriented to manifold with negative Euler characteristic. Let pi hat be the set of all free homotopy classes of closed curves on S. In this figure, the loop alpha is freely homotopic to the loop beta, but not to the loop gamma. Next, we define the geometric intersection number. For alpha beta in pi hat, we write I alpha beta. This is just the smallest possible number of intersection points between some representative of A of alpha and some representative B of beta. Let's move on to the next slide. I'll show two important examples. In the first one, at first glance, the two loops alpha, beta seem to have two intersection points. Two intersection points. But by a free homotopy, we can reduce the intersections to 0, so the geometric intersection number of alpha and beta is 0. On the other hand, the second example is an important case where the geometric intersection number of alpha with itself is not necessarily 0, even though we take the same free homotopy class. In this example, the geometric intersection number is 2. So we have just defined the geometric intersection number. Now, to capture it algebraically, I will introduce some algebraic preliminaries. Let K be a commutative ring with commutative ring of characteristics 0. Let K pi hat be a free K module generated by the set pi hat. Goldman showed in 1986 that one can define a Lie bracket on K pi hat. This Lie algebra is called the Goldman Lie algebra, and the bracket is called the Goldman bracket. Now let me give the definition of the bracket. For alpha beta in pi hat, we first choose generic representatives of alpha and beta as closed curves on the surface. Then the Goldman bracket of alpha and beta is defined as the sum of overall intersection points P of these representatives. Each term is given by the local intersection number at P. multiplied by the free homotopy class obtained from the loop product of alpha and beta at P. Goldman also proved that this definition does not depend on the choice of representatives. Finally, by extending bilinearly, we obtain a bracket from k pi hat times k pi hat to k pi hat. Let's look at an example to make the definition clearer. In this figure, at the intersection point P, the local intersection number is +1. At Q, it is -1. For each of these points, the free homotopy class of the loop obtained from the loop product is shown in the figure below. Next, let me state a theorem of Goldman. Let alpha beta in pi hat, where alpha is represented by a simple closed curve. Then the Goldman bracket of alpha and beta vanishes if and only if their geometric intersection number is 0. Here, the condition on the right-hand side is a geometric condition, while the condition on the left-hand side is an algebraic condition. However, in general, the vanishing of the Goldman bracket does not imply that the geometric intersection number is 0. For example, as shown by Chas in 2006, here alpha and beta intersect at 2 points. Actually, the geometric intersection number is also 2, but the Goldman bracket is 0. So what we want to think about next is an algebraic condition that characterizes when the geometric intersection number of two loops vanishes without assuming that either of them is simple. Let me introduce some notation. Alpha to the m means the class that goes m times around alpha. Alpha inverse means the class alpha of alpha with the opposite orientation. With this notation, Chas and Kabiraj propose the following conjecture. This is still open. Let alpha beta in pi hat, and then the Goldman bracket of alpha plus alpha inverse with beta plus beta inverse vanishes if and only if the geometric intersection number of alpha and beta is 0, or beta equals alpha, or alpha inverse. Here in their paper, they interpret alpha plus alpha inverse as corresponding to the free homotopy class of alpha, forgetting its orientation, and that is the free homotopy class of an unoriented closed curve. Next, let me describe an alternative approach different from that of Chas and Kabiraj, which provides another algebraic characterization of when the geometric intersection number vanishes. let alpha beta imply hat, then if there exists m, if there exists a natural number m greater than or equals to 2, such that the Goldman brackets of alpha to the m with beta vanishes, and then the geometric intersection number of alpha and beta is 0, or beta equals alpha to the m. The corollary below removes this exception and gives a complete characterization. The geometric intersection number is 0. Let alphabet imply hat, then the following conditions are equivalent. Condition 1, and the geometric intersection number of alpha and beta is 0. Condition 2, there exist two distinct positive integers, m1 and m2, such that both brackets alpha to the m, alpha to the m1 with beta, and alpha to the m2 with beta vanish. Condition 3, and there exist two distinct positive integers, m1 and m2, and such that the bracket of alpha to the m1 with beta vanishes, and the bracket of alpha with beta to alpha with beta to the m2 also vanishes. Condition 4, there is a positive integer m. Sorry. Positive integer greater than or equals to 2, and two non-zero divisors, C1 and C2 in K, such that the bracket of alpha to the m with C1 times beta plus C2 times beta inverse vanishes. Now, let's return to the quiz from the beginning. To apply the corollary above and proceed with more algebraic calculations of the Goldman bracket, recall that there is a bijection between the set of free homotopy classes and the set of conjugacy classes of the fundamental group. Consider an orientable surface with boundary and negative Euler characteristic. Choose a maximal set of disjoint arcs, each starting at and ending on the boundary, such that the surface minus the union of the arcs remains connected. Label one side of each arc with a letter A, and the other side with the letter A inverse, B inverse, C inverse, D inverse. And the choice of arcs determines a minimal set of generators for the fundamental group of the surface. For example, the free homotopy class of the green loop, the green loop in the figure corresponds to the conjugacy class represented by the word ABC inverse. if we take the starting point here, A, B, C inverse. But if we take the starting point here, we get B, C inverse A. Note that depending on the choice of the starting point, one could obtain B, C inverse A or C inverse AB, but these all represent the same conjugacy class. By using these arcs, the Goldman bracket of alpha to the m and beta is computed as follows. In fact, for every natural number, the Goldman bracket vanishes. For example, the second and third terms belong to the same conjugacy class, but with opposite signs, so they cancel out. And the same happens for the other terms as well. Now, according to condition 2 of the corollary, condition 2 corollary, if there is two such integers, then alpha and beta can be separated by a homotopy. In fact, for this example, if we choose the representatives of alpha and beta appropriately, all of their intersections can be removed. Finally, let me mention what I have been thinking about. For a natural number m greater than or equals to 2 is the number of terms appearing in the bracket of alpha to the m beta equal to m times the geometric intersection number of alpha beta. In this talk, I presented a case where the number of terms is 0. And this concludes my presentation. Thank you very much for your attention.
Thank you, Aoi. Are there any questions for the speaker? So there was one in the chat that I will just read out. So what's the relationship between the plus operation and the operation under which we take the alpha and beta inverse on the slide with the Kabiraj 2022 conjecture?
This conjecture?
Yeah, what was how was the plus operation defined?
Plus operation defined. This definition is alpha. We defined the Goldman brackets like this, and extend by linearly, we get the Goldman bracket. So the definition of this is alpha beta plus alpha beta inverse, alpha inverse beta plus alpha inverse beta inverse.
See. Anybody else have any other questions? If not, we will thank Aoi again for the talk.